Hello and welcome to MT3. We are now on second order ordinary differential equations and in chapter 15 of Riley, Hobson and Benz. Okay, so let's have a look at this topic by first having, just laying out some general principles obeyed by higher order or any order ordinary differential equations. So an ordinary differential equation of order n will be written in this particular form. So you have some function a(n) of x times the nth derivative of y with respect to x plus some other function a(n minus 1) of x times the n minus 1th derivative of y with respect to x, etc., all the way to a0 of x times y, which we will interpret as the 0th derivative of y with respect to x. Okay, so when you see the 0 here, that means it's the function y itself. And in general, this will be equal to some function f of x, which is often called the source function. The reason it's called a source function is if you were working with a physical problem, this might be the driving force. So for a pendulum, this might be the kick you give it or the oscillatory system you couple it with. Doesn't matter, but this is the source function. More compactly, you can write this differential equation in summation form as I goes from 0 to n, ai of x, and y, the derivatives of y will be represented as y with curly round brackets I as superscript, and that's equal to f of x. So y with superscript round brackets of I is interpreted as the ith derivative of y with respect to x. And once again, y superscript naught is just equal to y. Alright, and then in operator form, we write it as the operator L hat operating on y to give you f of x, where the operator L hat is the linear operator. The sum I goes from 0 to n, the functions ai of x times the derivative operators di by dxi. Now this is a linear operator. If you haven't shown this, try and show it. We have seen how this can be done in one of our tutorials. Okay, now if f of x is 0, that means if our source function is 0, then this differential equation becomes the operator L operating on y is equal to 0. This is called the homogeneous equation. Okay, and it's called homogeneous because the dependent variable, in this case the dependent variable is y. Let's just remind ourselves the independent variable is x. All our functions, so y is a function of x. So y is the dependent variable and x is the independent variable. All these y's occur at the same power in this differential equation, and that's why it's called the homogeneous equation. So if you drop the f of x, if f of x is 0, then you have y appearing all the way to the power 1 in this equation, and that makes it homogeneous, of order 1 in fact. So when you solve this homogeneous equation, we've already seen this. Now this leads to the complementary function, and yc, the c indicates it's a complementary function. That means the operator L operates on yc to give you a 0. Now yc will contain n linearly independent functions. For the first order ODE, we've already seen that yc contains one function and one constant, and for an nth order ODE, it will contain n linearly independent functions and n undetermined constants. We'll see more about this soon. And for a second order ODE, therefore, you would expect to have two linearly independent functions in the complementary function and two undetermined constants. Okay. Now a particular solution to the inhomogeneous equation, if you have f of x present in the equation, then it's called inhomogeneous because now y doesn't appear on the right hand side, so this equation is not homogeneous in y. It doesn't have the same power of y in all terms. So a particular solution to the inhomogeneous equation is any solution yp of x that satisfies the inhomogeneous equation. Any solution will do here. Remember, at this point we haven't talked about boundary conditions at all. All we are looking for are solutions to this mathematical equation irrespective of the boundary conditions. The general solution to the inhomogeneous equation is y of x is equal to yc. This contains the n unknown constants plus yp of x, which is the particular solution, and there are no unknown constants in this one. So to determine the n unknown constants in yc, the complementary solution, we need n boundary conditions. And that's pretty much lays out general principles of any of the ordinary differential equations we will be looking at. So now a little bit more about each of these terms. We have said that the complementary solution, yc of x, contains linearly independent functions. In other words, yc of x is going to be some sum I goes from 1 to n of ci. Ci's are constants, we don't know what they are. And these yi's of x are functions of x which are linearly independent. And that raises the immediate question, why are there exactly n linearly independent functions in here? And how do we tell if a set of functions is linearly independent? And this brings us to another topic called Wronski's determinant. This is after Joseph Oene Ronski. He's a Polish mathematician, and he moved to France, where he changed his name from Ronski to Oene Ronski. I don't know why exactly, but you can find out on Wikipedia. All right, so here's what the formal definition of linear independence would be. This carries over from what we have seen before in vector spaces. A set of functions yi are linearly independent if the sum I goes from 1 to n ci yi is equal to 0. So this identity and this has to hold for all x in the range of the applicability of this differential equation. I take it to be a to b. If this is satisfied only for ci is equal to 0 for all I, then this is said to be linearly independent. And this is something you've seen before in finite dimensional vector spaces too. I have a caveat here. This is what this asterisk indicates. We do allow exceptions at isolated points. So it is possible, and it is possible for this sum to be even for linearly independent functions, that this sum can be valid. That means this sum can be 0 for non-zero ci's, but this will happen only at isolated points, and typically this will happen when the yi's are 0. That means when these functions yi's have roots. All right. More precisely, in a set, as I said, of measure 0. Now, measure 0 is a technical term from measure theory. All it means is that this set is, in some sense, infinitely smaller than the set AB of points. So if you're dealing with the numbers on the real axis, if these functions go to 0 for an integer number of points, that's fine. But you can ignore that blue statement for now. Alright, so what Ronski did was to make this whole definition of linear independency a practical one, and he did it as follows. You start off with the condition we began with. So 0 is equal to the sum I goes from 1 to n ci times dy i's. Now remember that this notation means yi of superscript 0, it's the 0th derivative of yi, which is just yi by our definition. So we start off with our definition. This is the first term. Then we differentiate the entire expression once with respect to x. You'll get the first derivative of the yi's now appearing here. And keep on doing this till you've differentiated it n minus 1 times. So now we've got n equations. You can write this in matrix vector form. So we have the 0 vector now is equal to this matrix of all these derivatives of yi's times the column vector with the coefficient ci in there. Now each of these terms in this matrix will be the I, so the aijth term in this matrix, if I call this matrix the A matrix, the aij is the I minus 1th derivative of the jth function, and you can check this to see if it's correct. Now here's what we're going to do. If A has an inverse, so let's have a look at this. If A has an inverse, then we can operate with this inverse on both sides of this equation. So 0 is equal to A times C. Operate with A inverse on the 0 and A inverse on the A times C. You will get A inverse operating on 0, which gives you the 0 vector. That's equal to A inverse operating on A times C, which is just C, which means C, the vector C is 0, or the Ci's are 0 for all I. So, in other words, if we define Wx, now when is the inverse of the matrix exist? It exists when its determinant is non-zero. So now I'm going to define the Wronskian. This is called the Wronskian, W of x. It's generally a function of x, which is equal to the determinant of A. When this Wronskian is non-zero, then the Ci's are equal to 0 for all i's. And what this means then is that the yi's are linearly independent, because that was what we had put down as our definition of linearly independency. If the only solution is Ci is equal to 0 for all I, then these set of functions are linearly independent. So here we are then. If the Wronskian, which is defined to be the determinant of this matrix A, is non-zero, and it's non-zero everywhere, then the Ci's are forced to be 0 for all I, and that implies that the set of functions yi are linearly independent. Once again, we allow non-zero terms, we allow some exceptions, so this can be 0 at isolated points. We don't care about those, as long as it's isolated points. So let's put this down more carefully again. So Wx is the Wronskian, and it's the determinant of the A matrix you've seen above. So case 1. If the Wronskian is not equal to 0 for all x in the range of this differential equation from A to B, except possibly at isolated points, then the set of functions yi are linearly independent. Case 2. If the Wronskian is 0 at isolated points, this does not prove linear dependency. But if the Wronskian is 0 for all x in this range, then the set of functions are linearly dependent in this range. Alright, let's see how this works in practice. So here's the first example. We take two functions. y1 is sine of wx, or omega x, and y2 is the cosine of omega x. So the first derivative of y1 is omega cos omega x. The first derivative of y2 is minus omega sine omega x. We can construct the Wronskian. The Wronskian is defined to be, since we have only two functions here, we differentiate this once only, and we get a 2 by 2 determinant. So the first row contains the functions themselves. The 0 indicates there's no derivative. The second row contains the first derivative of these functions. Put them in there, compute the determinant, and what you will end up with is minus omega. Now if these omegas are non-zero, then this is not equal to 0. In fact, it's a constant in the range. It doesn't matter what the range is. So the Wronskian then is not equal to 0 for all x, and therefore y1 and y2 are linearly independent. Now I put a question here, but there is a relation between these two functions. Sine squared omega x plus cos squared omega x is 1. So how come they are independent? Think about it. Let's take another case. Now we have three functions, phi1, phi2, and phi3. Phi1 is e to the x, phi2 is e to the minus x, phi3 is the hyperbolic cos of x, which is e to the x plus e to the minus x over 2. Now I hope you can now see where this is going. We know that this set is linearly dependent. Alright, so I'd like you to show that the Wronskian is given by this determinant here, and show that this determinant is 0. Now you don't need to evaluate the determinant to show that it's 0. You can show it in using the determinant manipulation techniques you have learned in previous mathematics courses, or look at Riley, Hobson and Benz to see what they are. Okay, and it's going to be 0 for all x. Now since the conclusion would be, once you have shown this, the conclusion would be that since the Wronskian is 0 for all x, in fact in an infinite range, therefore these three functions are linearly dependent on the entire real line. Right, so that's how that would work there. Now let's have a look at some uses of the Wronskian. 1. Can an nth order homogeneous ODE have n plus 1 linearly independent solutions? Remember what I said earlier is that an nth order ODE would have exactly n linearly independent solutions. So let's ask if it can have n plus 1. Can it have more? We're going to answer this not generally. You'll find a general proof in the book by probably Arfkin. I'm not sure where it is. But let's look at the proof for a second order ODE. So we've got a second order ODE of this form, y double prime plus some function p of x y prime plus some function q of x y is equal to 0. And the question is, can this have 3 or more linearly independent solutions? So let's assume it has 3. So the 3 linearly independent solutions are y1, y2 and y3. We construct a Wronskian. The Wronskian would be first the functions themselves in the first row, then the first derivatives of the functions, and since the 3 of them, we will take the second derivatives also. So we have a 3 by 3 determinant here. And this must be non-zero for all x in AB except at possibly at isolated points. Okay. Right, but now we know from the differential equation that there's a relation between the second derivative and the first derivative and the function. So from here, if you put y1 in the differential equation, we get y1 double prime is equal to p times y1 prime plus q times y1, and that's equal to 0. Therefore, y1 double prime is equal to minus p y1 prime minus q y1. Similarly for y2, y2 double prime will be equal to this, and again for y3, y3 double prime will be equal to this. Now we can put those in the determinant, so we must have 0 is not equal to, the Wronskian is not equal to 0, and the Wronskian itself is given by this determinant, where now I have replaced the second derivatives by these expressions here. So the first 2 lines remain the same, and then we have the second derivatives now appearing in their alternate form. Well, now if you look here, this last row is simply a linear combination of the first 2 rows. Therefore, the determinant is 0. Because whenever you have one of the rows or columns as a linear combination of the others or some others, then you have the determinant to be 0. So we have 0 is not equal to 0, and that's a contradiction. That's what I've indicated by these opposing arrows. So we have a contradiction here. Therefore, a second order homogeneous ODE cannot have 3 or in fact more linearly independent solutions. But that leads us to another question then. Can a second order homogeneous ODE have only one linearly independent solution? Now what I'm going to do is answer this not completely rigorously, because I'm not sure what a rigorous proof would be. But I'm going to argue as follows. So we will show that given one solution y1 of x, we will be able to construct another solution y2 such that y1 and y2 are linearly independent. Okay, so that's what we're going to do. And this leads us to Abel's formula, or the formula for the second solution. This is Niels Heinrich Abel, who has done quite a lot in maths, and this is one of his results. So now we are dealing with the same kind of second order ODE, y double prime plus p of x y prime plus q of x y is equal to 0. And let's assume that we have 2 linearly independent solutions, y1 and y2. So we know that the Wronskian given by y1 and y2 in the first row and y1 prime and y2 prime in the second row, that's equal to y1 y2 prime minus y2 y1 prime. We know that this Wronskian is not equal to 0 except possibly at isolated points. Now I keep saying this, eventually I'm going to stop saying this, but I want to drill it in. Okay, fine. So now let's differentiate the Wronskian. The Wronskian, first derivative of the Wronskian with respect to x, just use the chain rule on these 2 guys here, and that ends up with as y1 y2 double prime minus y2 y1 double prime. And now we use the same substitutions we saw earlier. The second derivatives can be written in terms of the first derivative and the function, and the functions p and q. Same here. Put that in, and this then comes into the nice form that the first derivative of the Wronskian is minus p of x. This is the function of x times y1 y2 prime minus y2 y1 prime, but this is the Wronskian. So the derivative of the Wronskian is equal to minus p times the Wronskian. And now we can solve this. So dw by w is equal to minus p dx. Integrate from x naught, sum x naught to x. X naught will normally be the one of the bounds of the applicability of this differential equation. And what you end up with is, I'd like you to just convince yourself that this is the solution. The steps are here. The Wronskian as a function of x is given by some constant. This is the Wronskian at x naught, so this is going to be a constant, times the exponential of minus the integral from x naught to x of p of x prime dx prime. So once you have defined your differential equation, where is it? There it is. And once we know what this function p of x is, it's the function in front of the first derivative, then the Wronskian is in fact defined to within a constant. This is the constant. So the Wronskian is defined to within a constant. Now, this has puzzled me, and I don't have a solution to it. The Wronskian depends on p of x only. Why not q of x also? I don't know, and if any of you find out, please let me know. Alright, so now what Abel went on to do was as follows. He said, well, the Wronskian itself, which is y1, y2 prime minus y2, y1 prime, it can be written as y1 squared times d by dx of y2 over y1. Just evaluate this using the chain rule and you'll get this. So what we've got then is d by dx of y2 over y1 is equal to the Wronskian divided by y1 squared. And you can integrate now to get y2. The second solution is y1, the first solution, times the integral of the Wronskian divided by y1 squared. This is the second solution, plus some constant. Or, I've just written it out in full form. The second solution is the first solution times the integral of 1 over y1 squared. Then you have the Wronskian, which you can now write down as this exponential. Now the Wronskian has a constant, the w of x naught, but the constant just gets pulled out of the integral, and frankly we don't really care about constants when we define our functions. Any multiplicative constant will just be absorbed in when we solve for the boundary condition, so that's immaterial. And then we have another constant here, because when we perform this integral, this outer integral here, we get a constant. But this constant would simply multiply y1. And I want y2 to be independent of y1, so we don't want any term which has a constant times y1 appearing in here. So we'll drop this constant too. Okay. As a special case, if the function p of x is 0, then the Wronskian is 1. P of x is 0, then we get the exponential of 0, which is 1. So then the second solution takes the simpler form of y1, the first solution, times the integral of 1 over y1 squared dx prime. Let's take an example and see how this works. We'll take a familiar differential equation, d squared y by dx squared plus y is 0. In other words, p of x is 0. That means we have this case here. And q of x is 1. If we take our first solution to be y1 of x, which is sine x, please check that this is a solution. We need to find the other. So y2, the second solution, would be we just use this formula. We just plug in sine of x in here. So what we end up with then is we need to evaluate this integral. This integral is the integral with an upper limit of x of 1 over sine squared x prime dx prime, and this is simply minus the cotangent of x. So we get the second solution is sine of x times minus the cotangent of x, which is minus the cos of x. Now the sign does not matter. The sign is just it's immaterial. What we have is the function cos of x. We started off with sine of x. We've shown that there is a second solution. It's the cos of x, which is exactly what we expected. If you look at this equation, it's a harmonic oscillator equation. So you have two solutions, sine and cos. Right. So back to the question. Can a second order homogeneous ordinary differential equation have only one linearly independent solution? I think the answer is that if you say there's only one, I can always construct another using the Wronskian and using Abel's formula. And we've shown it for the sine and cosine case. You can show it more generally, and I've got an exercise for you. So this is not the most general exercise, but this one simplifies life a little bit. So if p of x is 0, then the two solutions are y1 and y2 given in terms of y1 using Abel's formula. Show that these two are linearly independent. That is, given y1, you can always construct y2 such that the pair y1 and y2 are linearly independent, which means the second order ODE will have two linearly independent solutions and no more than two. We've shown that there can be no more than two from the Wronskian. We've shown that there will be two and not one because of Abel's formula. Now this can be generalized, and on Wikipedia, in fact, there is a generalization of this whole result. Have a look at it if you're interested. But this is what I wanted to say over here. So let's go to the top. We have looked at a few general ideas about higher order, or we focused on second order, but in general higher order ordinary differential equations. We have looked at how many solutions you will have, how many linearly independent functions you will have in the complementary solution. We have looked at the Wronskian and how it can be used to determine if a set of functions is linearly independent, and how it can be used to find a second solution given one of the solutions. Alright, so we're going to stop here, and in the next tutorial we'll look at more examples of how to solve differential equations more specifically. Thanks for watching.